So let's study gradient descent in more mathematical detail. Our error function is a function of the weights, and it can be graphed like this. It's got a mathematical structure, so it's not Mount Everest anymore. It's more of a Mount Matterhorn. So we're standing somewhere in Mount Matterhorn, and we need to go down. So now, if the inputs of the functions are, say, w1 and w2, and the error function is given by e, then the gradient of e is given by the vector sum of the partial derivatives of e with respect to w1 and w2. This gradient actually tells us the direction we want to move if we want to increase the error function the most. Thus, if we take the negative of the gradient, this will tell us how to decrease the error function the most, and this is precisely what we'll do. At the point we're standing, we'll take the negative of the gradient of the error function at that point. Then we take a step in that direction. Once we take a step, we'll be in a lower position. So we do it again, and again, and again, until we are able to get to the bottom of the mountain. So this is how we calculate the gradient. We start with our initial prediction y hat equals sigmoid of wx plus b. And let's say this prediction is bad because the error is large since we're high up in the mountain. The prediction looks like this. Y hat equals sigmoid of w1x1 plus all the way to wnxn plus b. Now the error function is given by the formula we saw before. But what matters here is the gradient of the error function. The gradient of the error function is precisely the vector formed by the partial derivatives of the error function with respect to the weights and the bias. Now, we take a step in the direction of the negative of the gradient. As before, we don't want to make any dramatic changes, so we'll introduce a smaller learning rate alpha, for example, 0.1, and we'll multiply the gradient by that number. Now, taking the step is exactly the same thing as updating the weights and the bias as follows. The weight wi will now become wi prime, given by wi minus alpha times the partial derivative of the error with respect to wi. And the bias will now become b prime, given by b minus alpha times the partial derivative of the error with respect to b. Now this will take us to a prediction with a lower error function, so we can conclude that the prediction we have now with weights w prime and b prime is better than the one we had before with weights w and b. This is precisely the gradient descent step.